Hi, and welcome to the Hive series on PCB design with KiCAD. My name is Ben, and in this part 3, I'll be giving an overview of the circuit we're going to be designing a board for and go through the part selection for this board. I don't think you need any electrical engineering knowledge to understand this material since I'm not doing any actual theory. Most of it is just why I picked the various parts and how you might do so for your own project. So in that case, let's go into it. So what are we actually designing a board for? It's basically a flashlight, or more technically you might call it a battery-powered switched LED circuit. We're using a chip called an LED driver that provides a fixed and stable current and voltage at the output for driving a number of LEDs, more than one. It's more stable than a battery and a resistor, and it can boost the input voltage up to drive many LEDs both in series and parallel. We'll use a simple push-button tactile switch in a single pole, single throw, normally open configuration that will turn on and off the circuit, or really enable and disable the LED driver. And the power will come from a single coin cell battery. Okay, so for those of you who don't know, or like me, always forget about switch jargon, this is a brief rundown. The number of poles describes how many circuits the switch controls. This is not how many outputs, but it's literally how many circuits or how many electronic pathway selections. You should be able to see the difference between the first two on the right, which are both single pole, that's single pole, single throw, and single pole, double throw, versus the second two that are double pole. So the double pole single throw has two circuits, two separate circuits. The double pole double throw also has two completely separate circuits. Each pole can either be latching, where the state is maintained like a light switch, or momentary, where the state only changes for the duration of the actuation, like a keyboard key, for instance. The second important term is the number of throws, which describes the number of outputs per pole. So the first switch, the single pole single throw, controls one circuit with a single output. The second switch, the single pole double throw, has one circuit with two outputs. Looking at the third is a double pole single throw, so it's two circuits, each with one output, and so on. Throws can be normally open, meaning disconnected, like the button on the lower right, or they can be normally closed, meaning connected, like the button on the lower left. One of the terminals will be common as well, meaning always connected to the input, and is mostly reserved for or relevant for double throw, meaning two output switches. There are also many different types of actuation, including toggles, rockers, buttons, sliders, and more. And switches are typically named by the number of poles and then the number of throws. So for instance, single pole, single throw, or a quad pole, double throw, like that. With shorthand being SPST for single pole, single throw, or 4PDT for quad pole, four pole, double throw. Single throw switches will often also have a notation for whether they're normally open or normally closed, meaning NO or NC. So before we begin CADing, you'll want to either have your parts on hand or know that they're available. Otherwise, you could be very sad later when you've spent hours designing and routing only to find that the packages or parts you need don't exist. By having these parts ready, you're ready to generate and find the correct footprints as well, which will also save you future headache. This is often a very time-consuming process, but it's really important for an operational board, so definitely take the time to pick good components that will work for your design. You always start with figuring out what your driving factors are. So this design was driven by a few factors, which are in no particular order. I arbitrarily wanted to use a coin cell battery, mostly because they're small and available, and the holders use non-standard footprints for practice. They also have enough voltage that I could have driven a single LED on one, though I chose not to. I wanted to use an integrated circuit to demonstrate locating symbols and footprints online. I wanted a low but varied component count to demonstrate the different symbols and footprints that we have or that are available. I wanted it to be low cost in case somebody actually wants to fabricate this. And finally, I wanted this to be conceptually easy because you shouldn't need to know electrical engineering to go through this board design process, or at least for this design. So how did I locate these parts? Primarily, I tried to find parts that were readily available in the Hive. These included resistors, capacitors, inductors, that's R, C, and Ls, LEDs, the switch, the battery, and its holder. Any other components, primarily the integrated circuit, were sourced from DigiKey, which is mostly because I'm familiar with them and how to navigate their website, but I'm certain that I could have found most of or any of those parts on Amazon, Mouser, or any other supplier of your choice. So what were the parts that we actually chose? The battery is a CR2032, a really standard coin cell, lithium primary, 3-volt nominal, and it's available and I chose it because, again, it's Hive available and it's small. The battery holder is also the standard one that we've been using at the Hive. I did have to hunt a little bit for the drawing, but we'll talk about that much later. The switch is a standard 6mm push-button tactile switch, which you've all used before, even if you didn't know you were using it. It's very standard. It's momentary on button, and again, it's Hive available in a multitude of different colors as well. And the LEDs I also standardized to a 5mm clear domed through-hole LED, which is, again, the very standard LED that you've seen before. We also have that in a number of different colors and actually in kind of super bright models as well. The LED driver was a little bit more involved, which ICs normally are because they have more parameters. There wasn't one available at the Hive, so I DigiKey filtered 4 in order. In stock and active status, which is always a good filter to set. A minimum supply voltage of less than or equal to 3 volts so that it worked with the battery. A surface mounted package, which was an arbitrary decision, but that one that was hand solderable. So nothing super tiny or BGA style packages where BGA has the little balls underneath the plastic, which are impossible to solder by hand. Also no leg packages like QFNs, if that means anything to you. And lastly, I chose boost topologies only because I had a 3-volt battery and I needed to increase the voltage up sufficiently to actually drive 4 LEDs, since each LED drops roughly 2 to 3 volts. So I would need at least between 8 and 12 volts at the output to actually drive those LEDs successfully, which is what boosting is. This resulted in 26 options. So how did I actually down select from this when they are all pretty similar? Frankly, cheap and available is usually good, but also reading the datasheet is really, really important because suppliers can definitively be wrong in their filters and in their search, their kind of outputs. So it's really important to double check what the supplier says with your datasheet and look through the datasheet for any additional useful bits and bobs that can be either beneficial or whatever the opposite is of beneficial to your design. So I chose this Richtech USA part called the RT4526 GJ6. The GJ6 is actually not relevant to the part name, but doesn't matter. And I chose this because for a few reasons. First, it was on the cheaper and available side. Second, it had an enable pin, which is a little bit cleaner in my eyes rather than kind of just disconnecting the power, although it does mean that there's a little bit of power loss even when it's off. And third, the datasheet provided both recommended components as well as a typical application schematic like a circuit and some layout guidelines and an example layout. Very helpful for when you're actually doing your layout because it means you have to do, well, less work. And finally, there were no available symbols and footprints, which was really good for this tutorial, but terrible for design work. Normally in your design, you'd look specifically for parts that have readily available models, so you don't have to spend time waiting for requesting them or developing them on your own. So this is what the typical application circuit looks like on the right, and below that were some recommended components for that typical application circuit. The current through your LED is defined only by a single resistor. That's the R set on the lower right there. That drops 300 millivolts or 0.3 volts. So for 10 milliamps, which is roughly what you want through LEDs, that means that the R set is going to be 30 ohms. For simplicity, I didn't select RSET or the capacitors or inductors based on this specific part number. I actually chose them whatever was available in the Hive, though I kept the same values. The diode wasn't available either in the Hive or on DigiKey, so I actually selected a similar one that dropped a similar voltage and had a similar kind of maximum current rating. So here's the full circuit and part list. Don't worry about memorizing this or anything like that. I'll bring it back frequently as needed during the upcoming videos, though feel free to print it out if you'd prefer. And this is the bill of materials without any of the actual bill portion. We'll see this again later as well. And with that, we've reached the end of part 3, in which I introduced the circuit and went through the process of part selection. Hopefully this provided some insight onto doing this process on your own. A PDF, as always, of this video is available as well, linked in the description, and hosted on the Hive's Wiki. In the next video, part 4A, we'll finally get into the actual design with an introduction to KiCAD and KiCAD's schematic capture view, as well as placing basic symbols. See you then.